Well, I wanted to make a video about these, starting with these motors here. One on the left is a DC motor, and the one on the right is a universal AC motor. And the only difference between these two motors is that the one on the right has coils in the outer stator, and the one on the left has permanent magnets. And the DC motor, if you connect it to a battery, it'll act as a motor. But if you spin the armature, the permanent magnets are positioned, one's north facing inward, the other one's south facing inward, and it produces a DC current. So it acts as a DC generator. And you can do the same thing with these universal AC motors. The only thing is, to convert one of these universal AC motors into a DC generator, is the brushes back here. These brushes are usually connected to the coils on the stator. The current goes through, like, you got a positive line and a negative line, or a positive wire and a neutral line, and the neutral line connects to this coil, and then the other end of this coil would connect to one of the brushes. Same thing with the positive line. It makes to the other coil, and the end of that coil would connect to the other brush. So the way you turn this into a DC generator is that you would disconnect the coils from the brushes, okay, and you would connect the ends of these coils together. So you would have one positive wire, one neutral wire, and it's only going to, one line's going through one coil, and the end of this coil would go to the other coil, and so you would have two ends of one large coil, and taking up both spaces now. So then you would connect those two ends you have. Once you connect the two outer coils together, you would connect that to a battery source, turning these into electric magnets. And then all you need to do is spin the armature, and it would be a DC generator. So these are very similar motors, generators, but I've been exploring some of Tesla's old work, or some of his first inventions here, and I found this cool website. It's called TeslaProjectLabs.com, and they have really great layouts of all of his stuff here. Like, here's the Egg of Columbus, and they have a diagram there. They have the little components that are inside that make the rotating field from two-phase. And here's his magnetic field with a disc as a rotor. There's the induction motor, two-phase AC induction motor. But the one generator, or the machine, that I was most interested in was this one. It's they're calling it a Tesla two-phase AC generator with sync and async output. And if you look closely at the machine, you can see that it's very, very similar to these motors down here. Very similar. Mostly to the one on the right. But the only difference is, well, there's a couple of differences. This machine here isn't showing a commutator. If it does have one, you can't see it. It would be in the back. I don't see one in this picture, but what it has is 4 slip rings in the front. And this and no commutator, and this one has a commutator but no slip rings in the front. So I wanted to point out that if you were to take the commutator from this one and put it in the back of this one, and then have the 4 slip rings, so you'd have a commutator in the back, the 4 slip rings in the front, and the 2 outer coils. The 2 outer coils you would excite with a DC battery source running through the commutator, and then you would get a 2-phase AC output in the 4 slip rings. You see, and that would turn this machine basically into a rotary converter, like my rotary converter that I've shown in my other videos. My rotary converter has a commutator, and it has only 2 slip rings. This one has 4, and also the coils in the armature are a little bit more basic. This one has 2 coils. They're 2 coils that are 90 degrees to each other, versus the converter. Let's see here. The converter is more of a. It's got more of this kind of a thing here. See, it's got both. It's got 2 sets of coils, but a bunch of loops for each one. It's like it's got 1 set of coils for the DC current and 1 set of coils for the AC current. So as the DC current goes into the commutator and energizes its set of coils on the armature, the AC coils that are in the armature go around the north-south electromagnets. So the DC power would go through the commutator and these coils here, making them permanent magnets. These universal motors can also be run on DC power without having to disconnect the brushes. You can just run it directly on DC, but it usually takes a lot more power to run them, like anywhere from 60 to 120 volts DC to run these motors. But if you disconnect the outer coils and energize them separately with a battery, and then run a separate DC current through the armature, then you can get a much more powerful effect. You're running it like a shunt electric motor at that point. So that's what I'm thinking that could be used with the rotary converter. Is you can use some sort of a shunt motor control system to run the rotary converter from DC batteries. So you would have a means of controlling your input of DC power into the converter, and that would in turn control your AC output. Like if you started to run a lot of apparatuses on the converter and the speed of the converter slowed down, you can use a shunt motor control system to then increase DC current to make the RPMs go back up for the converter. And then once you have a setup like that, the only side effect that you're going to have at that point is heat. The more current you put into the converter, the hotter the coils are going to get. So if you have a means of being able to cool down the motor and its coils, then you can basically increase the amount of power that you get out of this thing. Even though if it's set, or its rating is at like 36 volts or whatever, you can put more than that in. You can put up to 60 or 90, all if you can control the heating side effects of these machines. But it's kind of starting to become clear to me how Tesla was, he went from building the induction motor to his 2-phase generator. And then I'm pretty sure he knew about these rotary converters, but history doesn't mention anything about that regarding Tesla and his work with, DC to AC rotary converters. But, the idea is sound. You know, you have batteries back then. You have no AC power. You have only DC power. You take that DC power, you turn it into AC power, but in order to have a means of controlling your AC power, you need some kind of a shunt wound motor control system. Then it controls the amount of DC power that goes into the outer coils, which is usually like anywhere from 3 to 6 volts. And then you put a larger current through the armature to get you're getting more of an efficient effect that way. Instead of running power through the coils and through the armature all together in one swoop, you put a separate DC power to these coils, then run a different DC current through the armature. The higher current. That increases your efficiency dramatically for these machines. So yeah, then all you got to do is figure out how to keep these things cool. You know, I'm sure back in the day when they built the 4-cylinder combustion engine for the first time, and they didn't have any radiator or any cooling system for it, they'd be like, all right, we got a running motor, now we got to keep this thing from overheating, so they put a radiator on it, you know, for the water pump and what have you. Right now we're at that point, I think I'm at that point anyway, with these DC motors and generators, and yeah, you can pump a lot more than its rated voltages into them, as long as you make sure you have a means of controlling its temperature. If they overheat, you'll melt the coils, but if you have some sort of cooling radiator system on it, you can put more than the rated current into them and have a lot more control over higher voltages. So anyway, I think this video's gone on long enough, so that's my little rundown on AC generators and DC